airplane fault detection using Bayesian networks.
Aboard aircraft, there are many sensors that detect faults in the engine. Our sponsors at Pratt & Whitney liken these to the onboard diagnostic system of your car. A signal is generated that says a specific test has detected some measurement that is outside of a safe or acceptable operating parameter. The detection of a fault does not tell you exactly why the fault occurred, it just tells you it exists. In the case of aircraft, this fault diagnosis is a very expensive process, and misdiagnosing a root cause can lead to a need for further repairs or even be potentially dangerous. It is with this in mind that Pratt & Whitney are asking the question, what if we could use our data to determine the root cause of engine problems given the fault codes? To this end, we were tasked with testing existing software that supports the building of Bayesian networks.
The primary goal of this project is to test the ability of different Python Bayesian network solvers to handle noise in a dataset and to still be able to detect key causal relationships between nodes given a network. Some important steps towards this goal include creating datasets with varying noise levels, testing these datasets in different Bayesian network solvers such as BNLearn, PGMPY, and Pomegranate in order to detect causality between the nodes in the network, and finally comparing the results of the different solvers to determine which one would be most appropriate to use when dealing with airplane fault detection.
In order to accurately and effectively test our solvers, our first step was to conduct extensive research on Bayesian networks, conditional independence and dependence, and D-separation. Once we developed a strong background on these respective topics, we picked our three solvers and created a simple Bayesian network to test each solver on. Our network consisted of 6 nodes that featured 3 types of connections, one-to-many, many-to-one, and one-to-one. We then developed functions for each node based on their parents. After we passed values through each of these functions, we added noise to each dataset through a random epsilon value and bin the results in order to discretize the datasets. Finally, we created a script to run each solver test file and compare the respective outputs in order to determine each solver's capabilities.
In order to determine the capabilities of the 3 solvers we were researching, we created multiple datasets with increasing amounts of noise. We ran each of these datasets through our different solvers to monitor their ability to detect causality when presented with data with large amounts of noise. The values on the left side of the table represent the probability of sprinkler given that rain is either 0 or 1. So we would expect that these two numbers will be different since rain and sprinkler should have a dependent relationship. The values on the right side of the table represent the same relationship but with the added condition that season maintains a constant value of 1. So we would expect the probability of sprinkler to remain the same since rain and sprinkler are independent. An analysis of our data reveals that BNLearn was the best solver for identifying these relationships, with PGMPY in second place and Pomegranate in last.
Compare datasets.py, what it basically does is it automates process of creating datasets with different noise levels at testing different Python solvers using those datasets. Okay, so first off we have the imports. These are necessary to use certain functions of the libraries. Sample count is the number of datasets that should be created. Noise levels range from low, medium, and high. Here are the directories. This is necessary for organizing the data and results. Here we are iterating through sample count and noise levels to create datasets to test. And here are the 3 functions we are testing the different Python solvers on.
Let's first take a look at the network we are focusing on for testing purposes. While this is a more general network, the testing techniques used in our scripts can be applied to Bayesian networks that include engine problems and potential faults, which is a more realistic model that a company like Pratt & Whitney would use. Now we can use the following command to run the compare datasets file. Once the program finishes running, we can see a test folder is generated. In the datasets section, there are 3 different datasets created, each with different noise levels, like Ryan mentioned earlier. These graphs that are also generated can help us visualize the noise. Here, the blue line represents the underlying function of the node rain in this case. The red points are the values in the dataset. The more noise added to the system, the farther the spread of the red points will be from the underlying blue function. Since this is a high noise dataset, there's a larger spread of points than the low noise dataset. Finally, we can take a look at the results. Each of these files contains conditional probability distribution tables for each of our tests. We test both conditional independence and dependence, as well as D-separation theorems to verify how well each of the solvers can detect relationships between nodes, even when noise is incorporated into the system. This is important because realistic datasets for engine faults can consist of very noisy data, and we still want to be able to diagnose the cause of faults when this is the case.